I teach natural sciences, grade 9, physical sciences, grade 11 and 12, and I teach grade 8 maths. Okay, so that is me in a nutshell. I absolutely love teaching. I started teaching more than 10 years ago. Very, very fortunate to have had amazing mentors as teachers. And yeah, someone sees from my hometown here. So I'm very glad to have you guys here. Very, very excited to walk this journey with you. And yeah, let's have some fun. Okay, now, before we start, we need to do a little bit of admin. Okay, so first of all, I am going to take you guys to the Google Drive. Okay, so this is what the Google Drive looks like in a nutshell. You will find at the bottom that there is the CAPS document for all of you really nerdy people out there who want to know what you're going to do forever and ever and ever. You don't have to download this. You don't have to print this, okay? It is just there for those of you who want to know. Then for next to it, you will see a grade 10 exam guidelines. I know it says 2015, but it hasn't changed, okay? It is still the exact same guidelines. They use this every year. So in these guidelines, you get all the definitions and things you have to know. So this is a really, really cool document to print out, to have on yourself all the time when you're having physical sciences. Okay, then I am going to share the link to the chat. There we go. Everybody got it. Then you'll see there's a folder that says week 2. And in that folder are the slides and notes from Monday, Tuesday, and today. Okay, I haven't uploaded tomorrow's. And here is a brief proposed schedule, okay, from this week. Okay, it is exactly the same drive as yesterday, Corley. All I'm doing is giving it to those who were not here yesterday. Okay, so guys, you can go here, you can download any of them. Please note that the slides is exactly the same as the Word document, so you don't have to download both. Okay, they're not there so that you have to have both. You'll notice yesterday's chat we had about the periodic table. I haven't managed to really constructively turn that into notes. So I've put the slides up there for you guys for so long, and you can go and see my crazy story about how to remember how a periodic table works. Okay, so now that everybody has that, what we're going to do today, before we start with molecular structures, I just quickly want to take you back to something we did yesterday. And if you weren't here yesterday, I promise you're not going to be lost, okay? I just want to make sure that you guys are all comfortable with something we did yesterday, and I want to show you a more scientific way of writing it. Okay, so yesterday, when we did writing of compounds, the one example we used was sodium and chloride. And we said that sodium has 1 electron in its valence shell, in its outer shell. And we said that chlorine has 7 in its outer shell. Right. Now, guys, if I have to draw this diagram every single time, it's going to take me very long. And when I then transfer the electron from sodium to chloride, now I can't see which of the electrons belong to chlorine and which of them belongs to sodium. Okay, so what we then did, and I'm pretty sure you guys have done this, oh my goodness, is we went, I say we, scientists, went and thought, well, is there not a better way that we can write this, keep the structure, keep the idea of this, but make it neater and easier? PJ, we haven't even started. Don't panic. Okay. So they then came up with Lewis diagrams. Anyone heard of Lewis diagrams before? No, I see lots of no's. I see a couple of yeses. Okay, cool. I see lots of yeses. I do see a couple of no's. So let's look at a Lewis diagram. Now don't panic, okay? Lewis diagrams, all that I'm going to do is instead of writing this electron like this, I'm going to give the electrons of sodium one symbol, okay? Let's go with a dot, a koliki. And I'm going to give the chlorine electrons a different symbol. So let's make all chlorines electrons crosses, okay? So now I've got one electron on sodium. So I represent that as a dot. Oh, you know what it is and you don't like it. Why not? Lewis diagrams are so cool. They show us how things bond. Okay, so now instead of drawing all my E's, okay, I'm going to draw 7 crosses. Can you see how much neater doing a Lewis diagram is than drawing E. Okay. Kyla wants to know if we're doing physics today or only chemistry. Only chemistry, guys. This whole week we're looking at chemistry. Okay. So, yes, yesterday I drew it like this. And you'll notice that in the notes, in the slide that I did from yesterday, I typed out the whole story. So if you can't remember the story, go look. Right? So yesterday and in the slides, I used this way of writing them. But in science, we don't draw the diagrams like this because it comes very confusing and like very cluttered and muddled and oh my goodness, okay? So instead, we draw Lewis diagrams. And Lewis diagrams is such a neat little way for us to show that sodium has given up the electron. It paid chlorine to go on the date. And chlorine took that electron and put it in her purse. And now she is negative. Okay. Yes, we are going to carry on with covalent bonds. Okay. What happens at the end of every day is I go and look through what we did. And then my brain goes, oh, maybe I should just tell you guys that we can't draw it like this with all the E's and that we use Lewis diagrams instead of doing it this way. That is why I'm starting with it. Okay, so yes, you are 100% correct. We are going to look at molecules, molecular, covalent structures. Okay, so here we go. Okay, right, we ready? So, today we're going to learn all about molecular structures. Okay, I see you guys remembered from yesterday. It makes me so happy. Okay, now, covalent molecular structures form when two atoms share electrons. Okay. Now that important concept there, sharing, is important. Okay. Sharing means that neither of the atoms in the bond is exceptionally greedy. Okay. They're not like your twin brother who just wants everything and takes it for them. They're willing to share. Okay, it's like when you go to the movies and you share a tub of popcorn. Okay, right? So when atoms share electrons, they form covalent bonds. Okay. Now molecular structures, sharing normally happens when I have two non-metals, okay? Two girls, right? They form a compound. Okay. Now, very important, and I'm sure you guys have done this, you can either have a polar or a non-polar molecule, okay? Poles. Where do I know that word from? Ah, my goodness, poles. We have two poles on the Earth. We have a North Pole and a South Pole, and they are on opposite ends. Magnets have poles, don't they? Yeah, they do. Yeah. So we can look at poles as being opposites of each other. No? Okay. So in chemistry, what things are opposites? Oh, I know. We have protons and electrons, right? So we have positives and negatives. All right. So when we have a non-polar, that means that there are no positive and no negative sides. Everything is neutral. But when we have polar molecules, we end up having spaces that are more positive and spaces that are less positive or negative. Okay, keep this in mind, okay, because it does play quite a big role later. All right. So the polarity, how positive, how negative, depends on something called electron negativity. All right. Where do we find the value electron negativity, guys? Come on, someone give me an answer. It's the thing we did yesterday. Wink, wink. Yes, the table. Vincent, well done. The electron negativity is stated in the periodic table. You don't have to remember it, okay? You just need to be able to use the coolest crib note that you ever get. Yes, it is the number on the side of the element, okay? Not all elements have electron negativity, okay? Like, for example, the noble gases, gosh, guys, they're like so chill. You know, they don't care if they give away electron. They don't care if they take electron. They don't have electron negativities, okay? Electron negativity is a value somewhere between like 1 minimum and the maximum is 4. Okay, right. Now, someone asked me, what is electron negativity? Electron negativity is how strongly an atom pulls the electrons that it's sharing towards each other. Okay, I'm going to say that again. Electron negativity is how strongly an atom pulls the electrons that is bonding it to another atom towards itself. So the bigger that number, the stronger that pull. The smaller that number, the less it pulls. Okay, so now think about it. We said that metals give away the electrons. Non-metals take electrons. Okay, so can you see how metals normally have lower electron negativities and non-metals tend to have higher electron negativities? Okay, right. In covalent network structures, ooh, new word. Miss P, ma'am, I lost you when we talked about polar and non-polar. Okay, hang on. Whoa. Right. Everybody okay with covalent bonds being sharing of electrons? And everybody okay with non-metals bonding with non-metals and forming molecules? Okay. Now, polar and non-polar is not a grade 10 concept. Okay. Polarity is much more prevalent in grade 11 and in grade 12. Okay, but I want you to start thinking about it, right? So, all elements have an electron negativity, okay? Electron negativity is how strongly an atom pulls the electrons that is bonding it to another atom towards itself. Okay, let's think about oxygen and hydrogen. Okay, oxygen has got quite a big electron negativity. So oxygen wants to pull the electrons towards itself. Hydrogen has got a much smaller, sorry, go back. Oh, yeah. Okay, I'll try again. Sorry guys, my tech finger just really isn't working today. Like not at all. There we go. Okay, so electronegativity is how strongly any atom pulls the electrons it is bonding with towards itself. All right, so the example I used was oxygen and what else? Hydrogen. Okay, so oxygen has got a high electronegativity. All right. Hydrogen has got a low electronegativity. Cool? Okay. Oxygen wants to pull all the bonding electrons towards itself. Now, hydrogen doesn't have that feeling. Hydrogen goes, I only have one. It's fine. I can give it to someone else. Okay? And so oxygen becomes more negative and hydrogen becomes more positive. It's still two nonmetals, okay? It's still two nonmetals. So it is still covalent bonds. Cool? Guys, I know it's hard. Don't panic about it. It's being sorted out. Stay with me, okay? Nonmetals, hydrogen and oxygen. So when they bond, they form covalent bonds, okay? But because oxygen, yeah, I'm sorry, I have 5 dogs, like just deal with the barking. Because oxygen is more electron negative, it becomes more negative when we have water, when oxygen and hydrogen bond. Okay, that's the only way, only reason why I'm talking about polarity. Okay. So, you got it? Polarity. Here we go. Now, we go from a non-metal and a non-metal bonding. Okay. Now we say, well, what about ice? What about diamonds? What about graphite? What about glass? Okay. All these things are molecules, but they are much bigger. We can see them. And that's where we get covalent network structures. Okay, cool. So I know a lot of these things can be very boring. I get this. But if you understand how all of these bonds form, then chemical and physical properties is much easier later. Okay, guys, come, let's work. So, covalent network structures are covalent bonds that extend throughout a crystal. Okay? They consist of giant repeating structures, and the atoms are covalently bonded to each other, not just to the thing that makes the bond. All right. So these giant covalent networks are formed in lattices. Okay, cool. So atoms in a crystal is arranged in a regular repeating pattern, and that is called a crystal lattice. Okay, now lattices can be formed in different ways, all right, and they have different shapes. Cool. But each of those depend on the atoms that are forming, how strong those bonds are, and what type of lattice or what type of crystal is going to be formed. Okay, so each type of lattice influences the properties of that material. Got it? Cool. So we're going to look at two carbon compounds, diamonds and graphite. No? And then we're going to look at silicon, and we're going to look briefly at boron. Okay, now guys, the stuff I give you today is all you need to know about it. Okay, lots of papers. Please go back one slide, Joe. Lots of textbooks go into a lot of detail on this. But what I've got in here is what you need to know. Okay, I've made sure that I look at the exam guidelines, at your Bible, and I've had a look at the CAPS document. Okay, so I know what is examinable and what is not. I promise. Kelsey, are you okay? Can we go on? Okay, I've got another man. Please wait. I can wait. Is crystal lattice a big section? Do you mean a big topic, or do you mean a big thing? You're gonna have to be much more specific. Like in the exam. Vincent, it is part of matter and material, and matter material is roughly about 33% of the whole paper. Okay, so no, it is not a huge section. Okay, but it is an important section. A lot of chemistry that you guys do now in grade 10 is very important going forward, grade 11 and grade 12. How many marks? So for this section, you're only probably looking about 5 to 10 marks. And I'm not just talking about moleculars. I'm talking about this, what we're doing, the giant covalent moleculars, as well as ionic, as well as the basics of metallic stuff. Okay, you think salt? Yeah. Salt is ionic. Okay. Think about a diamond. Think about the lead in your pencil. Okay, that's graphite. Okay, what page are we on in the Oxford? If you give me half a second, I'll find my Oxford and I will tell you. Page 112. These notes are on the drive, guys. All right, we're ready. Here we go. So, diamonds. What do we know? They're transparent. What does transparent mean? I can see through them. Okay. Doesn't mean I can't see them. It means I can see through them. Good job. I see lots of good answers coming out. You guys are really awesome today. Okay. Diamonds are exceptionally strong. Okay. And I don't just mean this from a financial point of view. Okay. I mean this from a physical properties point of view. I see a hand up. Remember to type me a message in the group chat. Okay. Sabrina, you're asking a very good question. So why don't I do that tomorrow? Okay, because it is part of covalent bonds, so we'll do that tomorrow. Okay, right. So diamonds are ridiculously strong. So they have a humongous melting point. Okay, like huge. Guys, I don't think you understand how hot 3,500 degrees Celsius are. Okay, and it is the hardest naturally occurring thing we know about. It might change, nah, but that is what we know. Can diamonds break? Yes, but the only thing that could cut diamonds is diamonds. Okay, so diamonds is used as a cutting tool. I know that sounds weird because yes, I am well aware of how expensive they are. Okay, but diamonds are exceptionally strong. How was the first diamond cut? Vincent, you know, that is a brilliant question. I would have to go and Google that. Okay, so this is what we know about diamonds. I want to show you how the carbon atoms in a diamond is put together. Right, you ready? Here we go. Now, the reason why diamonds has such a high melting point, guys, remember this is liquid. This is not even gas, okay? This is liquid. And because they are so hard is because they have a very specific form, not the form we can see, the form between the carbon atoms. Okay, so here is a 3D model of what the carbon atoms inside a diamond looks like. So if we take this little carbon atom over here, it is bonded to 1, 2, 3, 4 other carbons. And every carbon, every single carbon in a diamond is bonded to 4 other carbons, and it's got this cubic shape. Okay. And that shape there is why it is so strong. Lorata wants me to just go back. I can do so for you. Carbon structure is very different in coal. You are exactly correct. So the carbons, the bonding of the carbons in coal is similar, not the same, similar to the carbon bondings in graphite. So we're going to look at that in just a moment. Okay. Please just be careful. It's not exactly the same. Okay. Coal has lots of hydrogens in it too. Okay. But the carbon structures in coal and in graphite are similar. All right. Lorata, just let me know when you're ready to go. Guys, just remember, okay, that is why in the Google Drive, I put the Word documents in there for you so that you can download them. They're not big. Okay, there's like almost no pictures and things in them so that they don't use a lot of data, okay, so that it's easy for you guys to do. Allotropes is a very interesting question, okay? I'd have to go and Google that, Tamsin. To be honest, my science is way more headed towards organic chemistry. And in organic chemistry, we work with isotopes, okay, rather than allotropes. Okay, what causes the carbon to bond differently in different substances? It is about the electrons around it that the S&P orbitals that get chucked together. Okay, Simpiwe, I'm not going to email you guys the notes. I will quickly put into the chat again the Google Drive, okay? All the notes you guys can go and download from there. All right, so that is a diamond structure. Okay, so to change the shape of the diamond, I have to break all the bonds between the carbon and all the other carbons, keeping it in place. Okay, to make this thing liquid, I have to make these bonds soft enough that the atoms in between can flow over each other. Okay, and that is why diamonds are so strong, because of all of these bonds that I have to break, okay, or the bonds that I have to soften to make this more fluid. What about the carbon in the corner looking so slowly? That one over there, that is simply a key. Okay, the key, they simply give you that is carbon. Barking in background intensifies. I disagree. That is Jack Russell. That is not serious barking. Okay, the big dogs bark way harder than that. Okay, and yes, I know there's a human walking past. Don't panic, guys. All right, everybody ready? Go. So let's look carbon versus diamonds versus graphite. Got it? All carbon. Okay? Graphite equals carbon. Diamonds equals carbon. Right? But this is where bonding comes in and where bonding gets cool. All right? So graphite is black and soft. Think about it. It's your pencil, guys. Like it's the stuff that's inside your pencil. Okay. The atoms in graphite form strong covalent bonds with 3 neighboring carbons in the same plane. Okay? In the same plane. Not in this plane as well and in this plane as well. So, one carbon forms bonds with 3 other carbons here. Okay? And then all of these stacks of graphite come back down onto each other. So technically speaking, when you write with a pencil, the line you leave on the paper is a layer of carbon. Okay, so layers of carbon atoms have a hexagonal arrangement. What's the word hexagonal mean? Come on, what does the word hexagonal mean? 6 sides, good job. Someone asked if you need to write this down. You can, you don't have to. These notes are on the Google Drive, of which I've put the link in the chat. And for just in case, there's the link again. All right. Hang on, someone asked a really good question. Wait. Ma'am, does graphite conduct electricity? Now, I'm wondering why you asked that question. Okay? Okay? If you think about a metal, metals, lots of protons in a sea of electrons. Okay? And they can conduct electricity because the electrons are free to move. Now, if I do think about carbon, and the carbon atoms bond, and then I create these layers. Can I have a guess from you guys? Yes or no? Carbon or graphite conducts electricity? Good. Yes. Graphite conducts electricity because it forms these layers. And so the electrons in the graphite layers, okay, can react and chemically do it similarly, not the same, similarly to metals. Okay, diamonds don't, because each carbon atom is stuck in position and the electrons of that carbon atom keeps it in that position. Okay, right. Yeah, please don't try this at home, guys. Okay, no one's parents are allowed to come and trace me down and shoot me. Okay, so this is what graphite looks like. I have my layers and layers and layers and layers of carbons, okay? And each carbon is bonded to 3 other. What's the difference between lead and graphite? Okay. Lead is a metal on the periodic table. We haven't used lead in pencils since around about the 1700s. Okay, 1700 and something, they realized that coal writes better than lead. Cool. So they replaced the lead, which they did use to write with, because lead metal kind of looks a little bit like graphite, okay? They replaced it with graphite. And since I think it is 1930 somewhere, okay, lead has been not allowed in any normal stuff, okay? In the last 50 years, it hasn't been allowed in paint because it is, poisonous, difficult word there, but yeah. So lead is toxic to your body, and for some other bizarre reason, lead, like mercury, like quicksilver, easily comes through your skin. Okay. Why is it still called lead? Well, why do you call a tomato a vegetable? Okay. How toxic? Very toxic. Okay. Tomatoes are not a vegetable. Tomatoes are fruit. It has seeds. Okay, guys, you need to make sure you're very clear about the different words you use. Okay. It's like when you get onto a scale, you don't get your weight, you get your mass. Okay. So guys, I know this is an interesting conversation to be having. Okay. So just think about the words that you use and how the words you use is different to what the science definition is. Okay. I'm not trying to tell you that you've been taught wrong all your life. Okay. I'm just trying to show you that different words and different concepts have different meanings to different people. Okay. All right. So that is graphite. Now the bonds in that layer is strong, but the bonds between the layers are weak. So the layers can glide over each other easily. So when you draw a line with a pencil, the result is a layer of black carbon that flakes off. Okay, cool. We've got 2 more. You ready? These 2 go quick. We've got silica, which is also covalent. Oh my goodness. Now silica you find in glass. You find in quartz. Silicon, yeah. And you find it in sand. Okay. Silicon oxide is SiO2. So each silicon atom is bonded to 2 oxygen atoms. And interesting enough, each of these oxygen atoms is bonded to 2 silicon atoms. My spelling went out the window there. I apologize. Okay, so let's look at what silicon looks like in 3D. Cool? There we go. Now this is very similar to what diamonds look like. Okay, so they have similar properties. Got it? Okay. Then the last one we have is boron. And boron can have many different forms. Okay, so depending on the form it has, Lorato, do you want me to go back, Lorato? Lorato, is that far enough? Can I go 1 forward? Hey, don't have a go at her. Ma'am, these compounds are important for us to know for our exams. You need to be able to interpret pictures of them, okay? And more important is you need to understand why they form these big things. Vincent, you ask the same question everybody always asks. My answer is, I don't know. Okay. Is granite as strong as graphite? Granite is much stronger than graphite. It contains metals. Okay. Graphite only contains carbon. Granite is lots and lots of different things. Mr. 99, you asked if I can go back. So we are so far past graphite that I would have to go back to yesterday for that. If you look in the chat, there's the Google Drive. You open the Google Drive and you go and find today's slides. Okay. Will we be asked to draw these structures? No, it is unlikely that you will have to draw these structures. Okay. Loretta, I'm going to go to the next one. Oh, shame, Tyler. Okay, so this is the last one. Boron. Okay, so boron can have hexagonal like graphite, or it can have the cubic shapes of diamonds. So it depends on what its shape is. Okay, that will tell us. I see lots of interesting comments here. Now, guys, I have this conversation with my kids regularly, okay? If you are in grade 10, you no longer have to be in school. If you're going to take this subject, you better work, okay? So, I'm willing to work with you. I'm willing to give you my best every single day, okay? But what we are going to start doing, and I'm going to start asking the moderator to help me, is if you guys want to do science, okay, you need to actually work. Otherwise, I'm going to get you kicked off. Because I will gladly work with every single one of you here who wants to work, all right? I see some of my own learners in here, and I've seen them be quite quiet, okay, which I think is a little bit unusual for them. And I've seen like Vincent asking questions and Miss P asking questions. There's quite a few people who have been asking questions, okay? So what we're going to do from tomorrow is we are going to start kicking people off who don't want to be here. Man, even after this lockdown, will we have these online classes? That question was asked yesterday. We have put it forward to admin, to the people who organize, and they seem quite keen. But please note that there's lots and lots and lots of things that have to happen for us to be allowed to do that. So we have heard you, okay? We have heard you, but we are doing the best we can. Daniel, I really appreciate that. Okay, ma'am, will you give us activities? I will do. Okay, I will do. The thing is just with this stuff, it's very theory. Okay, will we write exams in lockdown? I don't know. Okay, I don't know. No one knows what's going to happen, guys. And I know that's a sucky answer, but everybody's just doing the best they can. All right, guys, I got a question earlier. Someone wanted me to look at covalent bonds, okay, and have a look at covalent versus ionic bonds, okay, and look at how it's positive, how it's negative, okay. So we're going to do that tomorrow, okay. What is boron exactly? Boron is a semi-metal. It's a metalloid. Okay. Ma'am, please give us homework. Oh my goodness. So I'm going to have to like prepare differently. All right, guys. Thank you so much for your comments. Now I know how to change my setting for you guys. Okay, and I will do so from tomorrow. I don't stress. All right. Thank you so much for joining. We have to sign off because there's more lessons coming. And so the admin for this lesson has to start another one. Okay. So tomorrow I will have lots more examples for you guys. I'll have you some homework and please go check out the Google Drive. I'll put more stuff on there. Okay. I will see you guys tomorrow, same time, same place. Bye.